central limit theorem. This is the most important result in the whole of statistics. What this tells us is that no matter what distribution the random variable in the population is following, whenever we are looking at the mean or average effects, those will always be normally distributed, no matter what the population is doing. So that means that instead of needing to know each distribution, whenever we are looking at averages or the average effects of something, we know that those will always be normally distributed. So the only distribution we need, if we're only looking at averages, is the normal distribution. And this simplifies everything for us, and moreover, it always allows us to ask questions about the average effects. And this is why statistics is such a great tool to answer questions. One thing with the central limit theorem though, is that if you do this mathematically, it's going to become cumbersome and very abstract very quickly. Instead, I'm going to use a graphical approach to show you what's going on when we start taking the mean of random variables. So once again, let's revisit our die. We have a 6-sided die, each state is equally likely, representing the 6 possible outcomes. So let's now roll this die 100 times and calculate the mean. We might observe that, okay, after 100 die throws, we would have expected to observe 16.7 of each outcome, because it's a uniform distribution. Each outcome should happen at the same frequency. But due to the random draw, we might note that in this particular case, we got too many 1s, 2s and 6s, and too few 3, 4 and 5s. But once again, this is a random realization, so of course we should get deviations from what we expect. So we know that when we pull a sample from a uniform distribution, the expected value is in the middle. So we know that the true value here would be 3.5. But in this particular example, when we calculate the sample mean, we got a sample mean of 3.36. So yes, it's very close to what we expected, because it's a best estimate we can get, so it should be a good representation of the true expected value. But due to the random draw, we will get deviations from what we expected. And here, the first step comes. So the sample mean is calculated from a random sample of random variables. So that also means that the sample mean should be random. And then the question becomes, if the sample mean is random, which distribution does the sample mean follow? So if the sample mean is a random variable, meaning that when we estimate the sample mean, we pull a sample of random variables, we equally weight each outcome. So since this is random, it should also follow some kind of distribution function. So what I want to do now, similar to how we could find the distribution empirically for the die rolls, the very uniform distribution, we should be able to use the same approach to find the distribution of the sample mean. So what I want to do now is that instead of sampling die rolls, I want to sample means of die rolls. So I want to roll the die 100 times, calculate the sample mean, and plot down the sample mean. I want to roll the die 100 more times, calculate the sample mean of those 100 die rolls, and note down that sample mean. And I'm going to do this a third time, a fourth time, a fifth time, and just continue calculating sample means from 100 die rolls. And each time I'm just going to put them into a plot. So after I have done this 10 times, we might get a plot like this. We notice that each bar represents one observation of a sample mean of 100 die rolls. And as we expected, most of them should be centered around 3.5, because that's the true value, that's what we're trying to estimate. But note, just due to randomness of the sample draw, we're gonna get deviations. So I'm just gonna roll the die 100 times more, calculate a mean, and then I'm gonna get 10 more sample means, and just add them to the plot. I'm gonna do it 10 more times, 10 more times, 10 more times, and just continue adding sample means to this plot. And if we get a large enough sample of the sample means, we should get a good estimate of the sample distribution, of the true distribution of the sample mean. And as you might note, now a pattern starts emerging. And it's probably a pattern that you start also to recognize now, because this is just the classic normal distribution. So note here, the gray area, is the distribution of sample means. And each sample mean has been calculated from rolling the die 100 times. So that means the sample size of each sample mean is 100, and we have done that 100,000 times. The red line is a normal distribution. And this is the only thing I want you to take away from this. This is the key insight you need to understand. The distribution of the sample means, look how closely they relate to a normal distribution. And this is the central limit theorem, because it tells us no matter which distribution you are calculating the mean from, the mean itself will always be normally distributed. And why the central limit theorem is so powerful is because we usually want to know the average effect, or what is the distribution of the average. Because it tells us that we can always use a normal distribution to evaluate the reasonableness of outcomes and interventions. And that's what I just want to show you next. How do we use this central limit theorem result to draw conclusions from our sample?